Everybody, we are and we would show our panel about Isaac Newton. Isaac Newton was an English mathematician, physicist, astronomer, theologian, alchemist. He was born in Grantham on 25 of December in 1642. He studied in 1661 at Trinity College of Cambridge, where he developed the infinitesimal calculus and the corpuscular theory of light. In 1669, he taught math at Trinity College of Cambridge, while in 1703 he became the Royal Society president. His essential work, Philosophiae Naturalis Principia Mathematica, in which he explains the three dynamics laws and the law of universal gravitation. Newton died in London on 31 of March in 1727.
Why does an apple fall to the ground? There must be a force which accelerates it towards the ground. If it reaches the top of the tallest trees, it must also act beyond, as far as the moon. So, why doesn't the moon fall on the ground? Newton imagined to shoot projectiles with increasing speed from the top of a mountain with a cannon. They would have fallen to the ground further and further, as Galileo had observed, until a projectile would have never touched the ground. That is to say, it would have started to orbit around the Earth. In fact, if planets do not orbit in a straight line, it means that there is an attractive force that curves their trajectory. Here is the clever intuition of Newton, which led him to formulate the law of universal gravitation. Two-point masses attract each other along the line intersecting both points, with a force which is directly proportional to the product of the two masses and inversely proportional to the square of the distance between them. The force of the first body on the second and that of the second on the first are actually the same. They follow the principle of action and reaction. They have the same value and opposite direction. However, just know that Newton could never do the calculations, because the universal gravitational constant g was measured for the first time in 1798 by Henry Cavendish using a torsion balance. We constantly notice the attractive force between the Earth and ourselves, and the gravitational force is the dominant force on a cosmic level. Think about the formation and interaction between galaxies and stars, the motion of satellites and heavenly bodies. How about a practical example? Tides. When the surface of the sea is closer to the moon than the center of the Earth, it experiences a greater attraction, thus the level of the sea rises. On top of that, the calculations of the gravitational force led to the hypothesis of the existence of a planet, Neptune, which perturbed the orbit of Uranus, before Neptune was actually observed in 1846.
Kepler and Tycho Brahe carefully observed the motion of the planets. Galileo studied the fall speed of the bodies and realized that, regardless of their mass, all objects fall with the same acceleration. While Newton used the results achieved by Galileo and Kepler to formulate a single law capable of explaining the movements of both celestial bodies and terrestrial bodies, of unified heavenly and terrestrial physics. It was the patient collection and examination of the observational data that led Kepler to formulate his empirical laws on the orbits of planets, and was the generalization of these laws that brought Newton to his universal theory of gravitation. This attempt was immensely successful, especially since the new law of gravitation soon showed that it could be applied to explain many other phenomena, from the precession of Mercury's orbit to the seemingly abnormal orbit of comets. With Newton, mathematics really became the language to describe the universe.
A great step forward was made by Einstein in 1919. Imagine a celestial object as a bowling ball and a planet as a marble, both placed on a trampoline. These will have a cone-shaped deformation because of the weight of the bowling ball. The marble will move towards it with a curved path. In the same way, a celestial object with a great mass deforms the space-time, making the surrounding planets move on curved paths. These perturbations of the space-time are called gravitational waves.
Hope you liked this video, and as Isaac Newton said, the truth is ever to be found in simplicity and not in the multiplicity or in the confusion of things. So enjoy the rest of the exhibition, and bye.
Bye.